Hello, my name's Brandon, and today I'm joined with Peyton, and we're going to talk about conventional sheet metal forming as a manufacturing process and how it compares to a newer, not as refined manufacturing process that is roboforming. So, in this video, some key points we're going to talk about. We're going to discuss what each process is and how they actually work. Then we're going to go over some advantages and limitations of each process and compare them to each other. Then we're going to talk about the cost associated with each process, such as upfront costs, costs over the long run, and evaluate what each process is better suited for. And then finally, we're going to assess them and give them a manufacturing readiness level to see how ready roboforming is to be implemented right now. So what exactly is conventional sheet metal forming? So conventional sheet metal forming uses a punch and a die to shape thin sheet metal into the desired die shape. Oftentimes it uses a hydraulic press to press the metal into the die shape, and this is normally done in a cold forming process. So the big advantage of this is that it's some simple shapes and the dies are geometrically simple. However, you can press a lot of sheet metal very fast, and it's quite a cheap process once the dies are made. So as we get into the advantages again, conventional sheet metal forming is very fast with high repeatability. So it's very suitable for processes with mass production. It has a very high dimensional accuracy, consistency across production runs, very smooth, surface finish is good, and it adheres to tolerances. And it's fully automatable, so you don't need anyone actually working on the process, just someone to monitor it and make sure everything's going smooth and all the metals formed correctly. Limitations is that design changes require completely new dies for even the smallest changes. This makes it very bad for prototyping or instances where you're going to need to make a lot of changes because a lot of the costs here lie in the cost of the dies. It's where we get into the very high tooling costs. So if you need to constantly be making new dies to adjust to changes you'd want to make, it's very expensive and not the use case here. Designing and machining new dies also could take several months, and this could just make your production run of whatever you're trying to make miserable if you're constantly purchasing new purchasing or making new dies that take really long to manufacture and are really expensive. You also need large presses to actually press and form the metal into the dies, and that all just adds to cost. So yeah, there's specialized materials for dyes as well, which could even farther add into your operating costs for this method. So thinking about costs of conventional forming over time, you have a very high upfront cost for tooling the dyes and making them. New dyes can range from tens of thousands to hundreds and thousands, depending on the part complexity and what you're trying to form. However, the process is very fast, so the machining cost is very low for high volume part batches. And like we said, it could be an automated process, so machining cost is very, very low. So in the long run, for very high volume part runs, it makes it a very efficient method. Tool maintenances and refurbishment costs can accumulate over time. Dies can wear, and that means that they need to be replaced. And like we said, they're very expensive and can take a long time to make. So it can add costs in it whenever they break.
So now let's get into exactly what roboforming is. Roboforming is a dieless sheet metal forming technique that involves a robot pressing a tool into the metal to form it into a 3D shape. It accomplishes this over many tool paths instead of just one instant die press. Now, there are many advantages and limitations associated with roboforming. Some of the advantages are that there is no need for expensive dies. There is no need to create a whole new die for any changes. Changing the final shape only requires modifying the toolpath and not any actual hardware changes. This makes roboforming ideal for custom one-off parts and prototyping because once again, you no longer have the need to create new dies for minor changes. Now, industrial-sized robots can work much larger pieces than traditional presses. This helps to save money since one machine can do many different part sizes. Now, there are several limitations that come with roboforming. One is that it is generally slower than conventional sheet metal forming. And due to sheet thinning, there is limited geometry that can be made. And then since the, the sheet is formed through many incremental tool paths, the surface finish is often poorer than that found with conventional sheet metal forming, and it leads to the net to needing secondary machining. Now, maintaining tolerances is also harder due to distributed loads. The loads cause vibrations in the in the robot arm, making it harder to maintain dimensional accuracy. Once again, there are many costs associated with roboforming, but the tooling costs are actually lower than that found in conventional sheet metal forming due to it being dieless. But the upfront cost is quite high because the robots are expensive and the operating costs are higher due to these longer machining times and the need for programming. So once again, this makes roboforming very cost effective for prototyping and not as much for mass production. Now, the forming tools undergo lots of contact. This leads to more frequent tool replacements. So even if the tip of the robot arm is cheaper initially than dies, these costs tend to add up a lot quicker than what you would find with conventional dies. And longer production times means more overall machining hours and power usage, which leads to increased energy costs. So what exactly is the manufacturing readiness level of roboforming? Well, it is seen to have an MRL of 6 in prototype situations and an MRL of 5 in high volume production. So this makes roboforming very suitable for low volume production, and it is not as widely seen for high production due to its slow cycle times. Now, robotic system manufacturers do obviously exist, but few suppliers specialize in incremental forming on an industrial scale. And process repeatability has been seen to be an issue with roboforming, but lately it has been improving, but not to the level that you would need for mass production and creating consumer products. So, is roboforming really ready for mass production? Well, it is seen that many standard manufacturing products have an MRL of 10 or pretty close to it. So this means that full rate production has been demonstrated in an efficient manner, but roboforming is only seen to have an MRL of 5 for mass production. This is not close enough to the maturity level that you would want to see for full implementation in factories. So roboforming is best used for one-off parts and is not currently ready for use in situations where mass production and very strict dimensional tolerances are necessary, despite its higher adaptability, since it can create many different parts without the need for changes in the actual die itself. So when looking at any source for roboforming, there's always a chance that biases make their ways into these articles. So to help limit this, we chose scholarly articles. So they were able to provide accurate technical details and data on process accuracy. Now, when looking at industry reports, they often try to sell roboforming and downplay its limitations. So these sources they needed a closer look to truly figure out where these biases were coming from and if the information being portrayed was as accurate as it was meant to be. So these reports were referenced to the scholarly articles just to make sure that the information lined up and nothing was being skewed too much. So this bias assessment helped to balance the strengths and limitations of roboforming, providing accurate information. So thank you again. That is the analysis on conventional sheet metal forming versus roboforming.